Okay, this is your first video in the water quality section. I've got this titled Water Quality and Treatment. That's the main two things we're going to focus on here. In your readings, that's chapter 20, and I believe it's called Water Pollution. And once again, there's quite a bit of information in that chapter you're not responsible for, so use your slides and your videos as a guideline for what I'm going to focus on. Also, there's quite a bit in these slides and videos that are not in your readings also, so that's going to be important. The first part here that is highlighted in red is the first set of slides and will be the first video, and so there'll be 3 sets of slides and 3 videos. The first set really is about the distribution and the use of water, and a couple things we'll talk about the structure of water, what happens to water in lakes at certain temperatures, and I will talk about acid rain again. Excuse me, even though we talked about that under the atmosphere section. The bulk of the material here is under this second set of slides, which will be water quality, and then a small set of slides also on water treatment. So let's jump right in here to the hydrosphere and look at an introduction here. So when you think about the distribution of water on the planet of the Earth, roughly you could think about 97% of it is salt water. Okay, I always tell students it's an easy number to remember. 97 and 3% roughly is fresh water. It's broken down a little bit more specifically here, but you get the idea. What a lot of people don't realize is most of your fresh water is tied up in ice caps and glaciers, about 2 of that 3%. And then most of the remaining that's really available to us is in groundwater. Most people tend to think, oh yeah, rivers, lakes, that's a lot of water. It really isn't in the grand scheme of things. You can see that from this figure. It's a very small percentage of totals. Lakes is very small. In fact, there's more in soil moisture than there is in all the lakes of the world. So you should have a general idea of the distribution of water on the planet. This is the hydrologic cycle. I'll point out a couple things here. This is pretty basic. It's probably something you were introduced to in middle school. But there are a few things I want to point out to you. One right off the bat is what an aquifer is. And I have a definition on another slide, but basically it's an underground reservoir of water. What a lot of people don't realize is this is not like a pipe underground. I don't mean a man-made pipe, but it doesn't flow like through an empty space. For the most part, an aquifer, the material there is going to be rock. Okay, something like limestone, a porous rock with water moves through cracks and also moves through the pores. It could also be broken up material, ground up sand and rock and stuff like that, but it's not a hole. Okay, so we're talking about the rate at which this stuff moves is really slowly over the course of time compared to some water that would move through a pipe. In some aquifers, you're looking at maybe 50 feet a year. There might be some that are moving like a couple 100 feet a year. Still pretty slow. So that's one I would point out to you what an aquifer is. You see here at the very top of the aquifer, which is the water table. So this water can rise and fall, in this case, based on how much water infiltrates and recharges the aquifer. Okay, some aquifers are actually confined and are under pressure. And they would have to have, you see down here, an impervious bedrock. They'd have to have an impervious layer above this here, which means the water table wouldn't be able to rise. It could theoretically drop if you're pumping it. But if it's under pressure like that, theoretically, if you put in a well and it's under enough pressure, that water could come flowing all the way out, or at least come rising up to a level which you could use it. So people that have wells for water, some of you might that live in rural areas, that's what you have. Springs are just kind of where where the water table can actually come to the surface. It's no longer confined. Here you see right here, the water table is confined. This would be an impervious area. So here it's restricted. Here you got an opening for water to come out. The rest of the stuff, you know from probably middle school, evaporation, transpiration, all of that type of stuff. But I did want to point out a few of those things there. So here's some definitions. Keep in mind that anytime we talk about the hydrosphere, we're talking about its strong connection with the geosphere. And in fact, geologists really define the geosphere as the hydrosphere being part of the geosphere. Some people distinguish those, non-geologists typically. Some more environmental scientists would say the hydrosphere and the geosphere, where geologists would say the hydrosphere is part of the geosphere. Some definitions: groundwater is held in a pore system of soil and porous rock strata. The aquifer is the geological unit that can store and transmit water fast enough to supply water to wells. And you have different zones: saturated and unsaturated. The unsaturated zone is also called by geologists the vadose zone. And if we go back here, this is the saturated zone. This would be unsaturated, above the water table. It's not saturated. When we say saturated, we mean all the pores, all the soil is completely filled with water. Up here, of course, it's going to drain down into here, so it's not going to be considered saturated. A couple terms then. The porosity is the fraction of your soil, if you will, or your rock, whatever, that is void space. Okay, so that's really just a fractional amount of pores that you have. Permeability is the ability to actually move water through the material. And an aquiclude, that's really just an impervious material. Low permeability prevents water from movement. So you have to have an impervious layer below the aquifer, otherwise it would just drain and you wouldn't have a steady supply of water. This is some information on rivers and lakes and things like that. A couple terms: a watershed. You actually drive around Middle Tennessee, you'll see signs like entering Stones River watershed, things like that. It's just the land area from which water drains to a particular water body. In this case, Stones River. Within water bodies, lakes and oceans and things like that, we have different zones. And you have the top zone, the middle zone, and then the bottom zone. Top zone is basically the region. Depends on the depth. It depends on the region of the world you're in, how much sunlight penetrates, and all that type of thing. The turbidity of the water. But basically, you wind up with a photic zone, which is where you have a lot of productivity. You're getting more photosynthesis going on than respiration. Then you have the aphotic zone, where the reverse is the case, and that's because you're not getting as much photosynthesis. And then you have the bottom zone, kind of the bottom welling zone, which typically has low levels of oxygen. Specifically in oceans, that photic zone could be a few hundred meters. And meters, roughly a yard, remember. The salinity of the ocean is 35 grams per liter, so we say that's 35%, because remember, 1 mil of water weighs a gram. And that's how we define the density, 1 gram per cubic centimeter, right? Cubic centimeter is the same thing as a mil. So 1 gram per cubic centimeter, or 1 gram per mil. So, if you will, a liter is 1,000 times bigger than a gram in terms of comparable, magnitudes. Therefore, 35 grams per liter will be 3.5% when you multiply that by 100. The pH of oceans is typically in the range of 8.1 to 8.3, and that's because of the dissolved constituents. They kind of create an acid-base environment that's slightly alkaline. These are the constituents that you see in seawater. That's where the 35 grams per liter comes from. This is in ppms, which is milligrams per liter, so we have to multiply by 1,000, so you get about 35,000 there. And you see the cation is sodium, and most of the anion is chloride, but there are other cations and other anions. But by far the majority is sodium and chloride. When you compare that to fresh water, to seawater, we said seawater is mainly these two, right? Well, fresh water is mainly these two, although there is quite a bit of magnesium you see, not much less than calcium. But the major anion is what's called the bicarbonate ion, or the hydrogen carbonate ion. And remember, we talked about this forms when CO2 dissolves in water. Well, that's all part of the acid-base system of natural waters. It can lose and gain hydrogen ions. Acid base can go either way. A base picks up a hydrogen ion So this would be in the movement of acting as a base. This would be acting as an acid, donating that hydrogen ion into the water. Here you're picking up that hydrogen ion. You also have solid calcium carbonate, precipitate and rock and stuff like that, that can dissolve and add to this. And then you have the CO2 coming from the atmosphere as a gas. So you can see how complicated this system is. They're all tied together and they're constantly kind of re-equilibrating and shifting all the time. So that's really important to understand. The next thing I want to talk to you about is some basic chemistry and characteristics of water that make it kind of unique. If you look here, we've got individual water molecules. This is a water molecule, this is a water molecule. What you see is these dotted lines in between. Now, these are the bonds we've always talked about, covalent bonds, okay, within your nonmetals. There's no metal here, so it's not an ionic compound. It's a molecular or covalent compound, and those are strong covalent bonds. But what makes water a liquid at room temperature is the fact that they attach to each other. If they weren't able to attach to each other, they would be a gas, like carbon dioxide. That is the difference between why something is a gas, a liquid, or a solid at room temperature, is the strength of what we call these intramolecular bonds. And that is the bonds between the molecules rather than the bonds within the molecule, the intermolecular bonds. So the stronger these are, really strong ones, you're going to have a solid at room temperature because there's not enough heat in the atmosphere to break that solid into a liquid. So that's why something like sulfur is a solid at room temperature. Water is a liquid, carbon dioxide is a gas. It's because of the strength of those bonds. Those hydrogen bonds are particularly strong in water, and they account for a lot of things. And one thing you see is the fact that what's unusual is that ice or solid water is less dense than liquid water. That's unusual. Most substances, if I freeze them and drop them in themselves, they will sink. Solids typically are more dense than liquids, and gases are the least dense. Well, water's unique that way, and that's critical for the evolution of life. I'll explain in a bit in the next couple slides, but what you see is this very open structure here because we can't squeeze another water molecule in here. There's nowhere for the bonds to go. So it creates this very open-like structure, which makes it has very low density, and also explains a lot of the shapes of snowflakes and things like that. So what happens is, what we see is that we look at the periodic table. We look at this group right here, oxygen, sulfur, selenium, and tellurium, and then we look at their hydrogen compounds, dihydrogen, so two hydrogens bound. We would predict water's boiling point based on this trend right here to be down here, but yet it's way up here. Why? Because of the hydrogen bonding. These guys don't hydrogen bond. Hydrogen bonding only occurs when hydrogen is attached to oxygen, nitrogen, or fluorine. And that is not the case for any of these other three compounds. So these bonds are not nearly as strong here for these other compounds. And that's why water is incredibly unique and why it's the fluid of life. And that's why we look for water in other places when we're looking for signs of life. We realize it's the fluid that is necessary as far as we're concerned for life to exist for lots of reasons, this being one of them. This shows you the specific heat. The way to define this is really just how much heat you have to apply to a substance for its temperature to change 1 degree C. And that's what these units are here. That's energy per gram of water per degree C. And you see water's much higher, liquid water, much higher than these other substances. Metals, of course, are very low. They change temperature very easily, and that's why we make our cooking pans out of metal, and they heat up quickly. But water, if you will, and that's why it's cooler next to a lake on a hot summer day. The air temperature rises quickly, doesn't have a high heat capacity. It's not on this figure. I forget what it is, heat capacity of air, but it's 1 or less. So the temperature of the air might be 95, but it might be 75 next to the water. It's nice and cool. It's also critical for fish because if the temperature changed that readily and got up to 95 degrees, well, fish would die. So it's critical in terms of the evolution of life. So what you see here now is what happens. Well, we're going to look at what happens. What this is the density of water. You don't have to concern yourself with the unit so much, but it is grams per cubic centimeter, but the scale here as a function of temperature. And water has a maximum density at 4 degrees C, and it's right at exactly 1. Now, as water starts to freeze, it doesn't freeze to get to 0 degrees C, but eventually the solid has to be less dense than the liquid, so the density of the water has to start to drop. That's why you see this part of the graph here. A lot of people would guess this part right here is that as the temperature increases, the water expands and therefore is less dense. No different than most materials. Your doors in your house expand in the summertime and they stick more. Why? Because the wood is less dense. It has expanded due to the heat. So this makes sense. As temperature increases, the density decreases. This is the part that's difficult to understand, but that's because of that structure of water, and ultimately the density of ice is down here somewhere. I've looked it up before, but I forget what it is. It's like 0.9, maybe 8, or even lower, 5, 0.95. So at some point it has to start to try to form as that density is dropping, as that structure we talked about is forming. And as a result, what we see in lakes in the summer, the densest water is down here at the bottom, nice and cool. And what turns out that cold water will hold, so in general, liquids hold more gases at low temperature. So when you think about temperature, you say, okay, if I want to dissolve sugar into my tea, it dissolves better when it's hot. So solids dissolve better in warm liquid, right? The opposite for gases. Higher temperature, the gases in that liquid, imagine them being more excited, right? At high temperature, and they escape. That's basically what happens. So cold water is going to hold more oxygen. More oxygen is going to be down at the bottom. Fish tend to like that area. And what we see here is a stratification of the water. Same way I talked about the stratification of the atmosphere, or how I told you how I used to do that demonstration in graduated cylinders with different liquids and having different density. That's exactly what happens here. Mixing going on here, but these two layers continue to separate and stay separated due to the different densities. Okay, and the densities are different enough that they're going to separate and stay separated. So you have an epilimnion, which, because it's close to the atmosphere, has a lot of oxygen, photosynthesis, so it's warm. And then you have the hypolimnion, which can actually hold more water because of the temperature, but it actually winds up being low oxygen because oxygen doesn't move very fast and it takes it a long time to get down there. And since there's no mixing, when it gets depleted down here, it winds up getting really low. So you can actually get cases in deep summer lakes in temperate regions in which the oxygen levels way down below are really low. So actually, I misspoke. I think I said a second ago the fish like it down there. That's not the case in the summer. In the winter, they do. Here, it's got too low of oxygen. If it's a deep lake, you only see this in certain depth lakes. If it's a very shallow lake, you won't see the stratification. So what happens over the seasons then? Come along fall, what happens is this cools. Eventually, the whole thing's the same temperature. Then it mixes very easily with movement of fish and movement of boats and wind because there's nothing keeping it separated because the densities are the same and you get a mixing. And then winter comes, and while you don't really get a stratification, you do have your densest water down here. This is where you're going to have a lot of oxygen because it holds more oxygen than up here. Also, you get the freezing up here because it floats. This actually forms an insulating blanket for the fish, keeps this at a nice reasonable temperature, 4 degrees C, and the fish will spend more time down here because it's warmer, and it still holds a lot of oxygen because it's cool water. Doesn't hold more than obviously 0 degrees C. I think I misspoke again there also. This is what we call an overturn. And then in the spring, the same thing happens again. You get another overturn in the spring, and then eventually that leads into this. So you can see here I've shown dissolved oxygen. low in the summer down here, as low as 1 ppm, as high as 10 ppm up there. Okay. The last thing I'm going to go through real quickly because we've already talked about this. Acid rain is mainly sulfuric acid combusting coal. This is the reaction that results in this, remember? And then the NO can go through several reactions, eventually form HNO3. This is the combustion temperature at high temperature, right? And then if you burn plastics, you'll get HCl. And these are some of the effects. I believe that's pretty straightforward. However, I will say that what happens is the acid, remember the main component of the acid is the hydronium ion or hydrogen ion. We could write it either way. And that will displace aluminum and other metals. And that could have a negative effect or a positive effect. A negative effect, well, actually, a negative effect in both cases. If it leaches out aluminum, the aluminum then becomes available, and that's toxic to fish. Or it leaches out other toxic metals that's bad to the fish, or it leaches away good metals that the plants like. Phototoxicity just means toxic to plants. I think the rest is I've talked about and is pretty straightforward. We've mentioned this. Burning coal. Jet stream brings it over in this direction. This is just showing you the different components there of acid rain. That really is the end of the video. So make sure you read your chapter.